Hi, I'm Eline Maaike de Weerd.
And I'm Clarkson.
I'm a final year PhD student at Queen Mary University of London.
And we're going to talk about the relativistic galaxy bispectrum.
With our collaborators Stefano Camera in Torino in Italy, Shyam Jolicoeur and Roy Martens in Cape Town in South Africa, and Obina Ume in Portsmouth in the UK. This talk will be largely based off this series of publications. So this is a series of papers that includes relativistic effects in the galaxy bispectrum and also looks at detectability of a bispectrum signal in future surveys like the SK and Euclid. The bispectrum will be an important probe for future surveys because they will be observing at higher redshift and higher precision. So to map the large-scale structure of the universe and to extract more information from that and analyze this information properly, we need to start looking at higher order statistics beyond just the power spectrum, which is very well studied and well known, and has so far mostly been used to constrain cosmological parameters. The bispectrum is the first of the higher order statistics. It's the Fourier-space equivalent of a 3-point correlation function, and as such it can help us constrain, for example, primordial Gaussianity, and by doing that we can maybe help distinguish between different models of inflation or other theories of the early universe. So because of that, the bispectrum will be a really important probe in these new large-scale structure surveys.
Let's have a look first at the power spectrum. Of course, the power spectrum is distorted by observing galaxies in redshift space rather than real space, and this distortion is just caused by the peculiar velocity induced by over and under densities, and this distorts their apparent position. So this is a well-known effect, and it affects the measured fluctuations by changing the measured galaxy over density delta G, which is a bias tracer of the dark matter density delta, and it adds on a gradient of a velocity term. And in Fourier space, this results in a change to the density contrast with a quadrupolar change given by mu, which is k dot n. Now, the relativistic contribution to this comes in at a higher order in powers of h over k.
If you then want to look at relativistic corrections, which really are suppressed on smaller scales, but come into play on larger scales, the leading type relativistic correction is a Doppler type relativistic correction. Plot on the right hand side on this slide is just the power spectrum for different scales k, which are plotted along the x-axis. And on the right hand side of this plot, so for large k, this corresponds to smaller or nonlinear scales, and things like this relativistic correction would be very much suppressed there because they are proportional to h over k. However, if you go to the left-hand side of this plot when k gets smaller, this is looking at larger scales because it's inversely proportional to real space distances, but also these relativistic corrections become larger at these scales. So if we're looking at these sort of scales, which future surveys will do, we need to take into account these relativistic corrections.
This adds in a term proportional to the radial velocity of the galaxies. So this is the term a times v dot n, and this appears on larger scales than the normal redshift space distortions. Then in Fourier space, this gives us a term which is proportional to mu, the angle between k and the line of sight vector, and a factor h over k, which suppresses the signal until we reach large scales. So in this expression, we're neglecting terms of order h over k squared, which appear on ultra-large scales, so well past the equality scale in the power spectrum, and we're also neglected integrated terms throughout this. So the basic idea is we take our observed distance, and instead of evaluating at the background redshift position, we add on this perturbation delta z, and this gives us a velocity correction corrected through a factor h prime over h squared. A full calculation gives us some extra terms in there, so there's the evolution of the co-moving density comes into play, changing the number of galaxies, and a magnification bias terms comes into play as well. It's interesting just to think about why the magnification bias comes into this picture. And the reason is that the number density is affected by the lensing convergence, and the lensing convergence has a Doppler correction, and this just arises from the redshift perturbation. So if we have a normal kappa expression, which is an integral over the density along the line of sight, the Doppler perturbation is just an additional term, but it's a local term added onto this, and this affects the magnification of objects. So on these heat maps for the Doppler convergence versus a weak lensing convergence, where we see the full sky signal at a redshift of 0.1 compared to a pencil beam at a redshift of order 1, we can see that at large scales and low redshift, the Doppler magnification term is important, and it comes into the number density contrast. So our galaxy overdensity in Fourier space then has this Doppler correction made up of a host of different terms, different contributions. The fact that we have a single line of sight vector projected on the velocity gives us a factor I times mu in Fourier space, resulting in a complex Fourier transform.
So the number density contrast in Fourier space is a complex quantity. So we have the real contributions from clustering and from peculiar velocities, which cause some distortion in redshift space, but also we get an imaginary contribution, an imaginary correction from the leading order relativistic corrections to this. However, if you look at the power spectrum of a single tracer, you will find that because this is delta delta of a single tracer, the imaginary part will cancel. And what that leaves you is a purely real quantity. So your power spectrum of a single tracer will still be real even if your density contrast is a complex quantity. However, if you would look at a power spectrum of two different tracers, these corrections, these tracer-dependent terms, they will no longer cancel because now your functions B1, your A, which is tracer-dependent, will not cancel anymore. So if you're dealing with two different tracers, you get an imaginary dipole in your power spectrum, which comes from these relativistic corrections, and your dipole is the L equals 1 contribution. And what this really means is that if you observe the power spectrum of two different tracers, it's less suppressed than in the auto power spectrum. So the power spectrum of two tracers, the relativistic effect in that is observable.
So if we just look at the dipole, this corresponds to the dipole in the two-point correlation function, which has been a bit more studied. How does primordial non-Gaussianity fit into this picture? Primordial non-Gaussianity also induces changes of order h over k squared into the power spectrum, and it does it through a change to the bias. So long wavelength modes from FNL modulate the higher frequency fluctuations and lead to a change in power spectrum of order h over k squared. So these relativistic Doppler corrections then come in at the same level as do primordial non-Gaussianity in the auto power spectra. Let's now turn to the bispectrum of a galaxy distribution.
For the bispectrum for a single tracer, we need to go beyond single order. We need the Doppler type effects up to second order. And at second order, you don't just get the Doppler effect at second order, but you also get couplings between these different sort of effects that you need to take into account in your number density contrast. And again, this is just looking at terms that are going as h over k. So what you get, as you can see here, is you get cross correlations between Doppler and density, Doppler and redshift space distortions, etc. And all of that needs to be taken into account.
We have a pure second order Doppler term, and then we have various cross terms which come in. So we have Doppler times density, Doppler times RSD, gravitational potential times density gradients, Doppler times a gravitational redshift gradient, gravitational potential times RSD gradient, and there's also a transverse velocity term which comes in through the gradient of the square of the velocity. All of the terms in this expression are projected along the line of sight.
Now, if you would look at all orders of h over k, so not just the leading relativistic corrections, it looks a bit more like this, which looks really quite intimidating. It's a very long expression. Then, if you want to calculate the bispectrum, it's a correlation between delta, delta, and delta second order. And this gives you the bispectrum, this b of g, which is a function of three wave vectors k1, k2, and k3. And the way you would calculate this is by having a product of Fourier-space kernels that incorporate your various effects that you need to take into account, times a product of power spectra plus cyclic permutations thereof. So in here, your k or k1 at first order is just whatever multiplies your first order delta, and your k of 2, so your second order, comes from the second order delta. And in there is a Dirac delta function, which basically just means that when you have these three wave vectors, k1, k2, and k3, they need to form a closed triangle in Fourier space.
Now, in the Newtonian approximation, we've seen that the first order kernel is just the bias plus f times mu squared, where f is the growth. At second order, this just gets extended with some extra RSD terms, some order 2 tidal bias terms, there's a squared RSD term, and order 2 density contrasts in the sort of standard F2 kernels. So the relativistic correction then just comes into a change to this Newtonian part with relativistic kernels coupled to Newtonian. So there's a second order relativistic kernel, K2D, and first order relativistic terms which come in. And if we truncate to order h over k, we have this relatively straightforward expression. So the Doppler corrections in Fourier space, we saw the first order one just goes like I times mu times h over k. The second order one is a little bit more involved and involves various contributions from different projections of the k1, k2, and k3 vectors along the line of sight in mu1, mu2, and mu3. So a bit of a mess, and very roughly it goes like h over k times the power spectrum squared.
So if you would look at the full kernel, the full relativistic second order kernel expanded in all powers of h over k, it becomes a lot more complicated and you get a mixture of real and imaginary terms. This is a complex kernel. And plotted, it looks like that, so you really see a departure at larger scales from including all powers of h over k. So on the left-hand side of the plot, you can see that this is just plotted for different triangle configurations. So because you have this closed triangle in Fourier space, you can look at like equilateral triangle shapes, or what we call squeezed, and one of the sides gets very small. So for the bispectrum, you can do a multiple expansion, which is analogous to what you would do for the power spectrum, for example, when you do a Legendre multiple decomposition. However, now because you have a triangle which has a specific orientation with respect to the direction of line of sight, you have two angles that you would need to integrate over. So it's no longer sufficient to expand in Legendre multiples. You can use, for example, something like the spherical harmonics. So the way you would do your expansion is pretty simple. It's a standard way of having your bispectrum times your spherical harmonics, and you integrate that over all angles.
So if we expand the bispectrum in spherical harmonics, we have a monopole and a quadrupole, which are real and given by the standard Newtonian forms. There's no Doppler type contribution in these. But we now have a dipole which is due to the imaginary part, and it vanishes if the leading order correction is neglected. So if we neglect the relativistic terms, the dipole vanishes, which means that it's a smoking gun of the leading relativistic correction to the bispectrum.
And that means that this is a smoking gun signal of the leading relativistic correction of the bispectrum. If you want to look at what it looks like when you plot it for given triangle configurations and given surveys, so here in the left panel, it's for an intensity mapping survey similar to the SKA. In the right panel, it's for a spectroscopic survey similar to Euclid. And this plot merely quantifies the sort of amplitudes that you would expect for the dipole with respect to the monopole. So the monopole here, the dotted line is Newtonian, and the solid line here includes all orders of h over k. So the solid line here does receive a relativistic correction at larger scales. So it receives a correction at larger scales. Of course, these effects are also at smaller scales. However, they are basically unobservable there, but you really only get a departure from your relativistic corrections at larger scales. So that's what's happening here. The right-hand side is similar. The zero crossings here are due to the tidal bias. B11 and B10 are the different orientations of the dipole, which are excited by the different triangle configurations. So the left panel is for a flattened or linear triangle, and the right panel is for a squeezed triangle. And what you cannot see here is that the amplitude of the dipole is really rather large with respect to the monopole, where the monopole is Newtonian is observable and the dipole is about 10% even at equality scales. So that means it's potentially detectable. That's already looking forward pretty promising. The next figure, again, left-hand side and right-hand side are for different types of surveys as denoted. And this is the dipole over an entire triangle range, so for different triangular configurations, as denoted on top of the plots with the little triangles. It goes from squeezed to linear configurations and vice versa. So what you can observe here is that in both panels, and this is a property of the dipole specifically, it vanishes identically for an equilateral configuration. What else you can see is that the different shapes of the triangles, different orientation, excite different orientations of the dipole. So the blue line or the red line are higher in amplitude or dominant depending on triangle shape.
If we look beyond the dipole, there's actually a hierarchy of relativistic multipoles. Generally speaking, all the multipoles get affected by the relativistic effects. All the odd multipoles are now from the imaginary part of the bispectrum, which is purely relativistic. Even multipoles consist of Newtonian parts plus these relativistic parts.
This truncates at L equals 8 and at M equals 6. Of course, there's also contributions for negative M, but these are very similar to positive M. They are related by symmetry. So you can see here for the dark gray squares, they are induced by Newtonian and relativistic contributions, and the white squares, so the odd multipoles, are purely there because of the relativistic contributions. They would be absent in just a Newtonian picture. What else is there? Denoted is when equilateral configuration is non-zero, and you can see that normally for every even M, for every value of L, you would have a non-zero equilateral configuration, except for the dipole where it is a special case. Also denoted is where you have non-zero collinear triangle configurations, which is only for M equals 0. Then this final figure for the multipoles is an exploration of the entire triangle space and the amplitudes of the multipoles over the entire triangle space. This is for in a spectroscopic survey similar to Euclid, and it's the first couple of multipoles which are plotted. So the even multiples, so for L equals 0 and L equals 2 here. This has contributions from Newtonian and relativistic effects, whereas the odd multiples, so L equals 1 and L equals 3, are purely relativistic, which is why they are slightly lower in amplitude. How else to read these? The top left corner of every triangle is the squeeze limit. It's where one of the sides, K3, goes towards 0. And the bispectrum tends to peak in the squeeze limit. It's why it's the warmest color closest to red. The top right corner of the triangles here is the equilateral limit. It's our old k1 equals k2 equals k3. And you can see that for the dipole, as we said before, this goes to 0. Then the bottom corner for every triangle is the collinear limit.
In fact, the higher order contributions, those of order h over k squared and higher, can mimic non-Gaussianity. And this is because primordial non-Gaussianity affects the bispectrum at order h over k squared. And if we look at the relativistic terms, these also come in at order h over k squared as well. So if you look at the monopole of the bispectrum, this will have density part, Newtonian RSD, primordial non-Gaussianity, and GR light cone effects. And these kind of interfere with each other. Now one can calculate from this an effective FNL, which is the FNL that you would get if you equated the relativistic bispectrum without primordial non-Gaussianity with a Newtonian bispectrum with primordial non-Gaussianity. And we can see that it corresponds to, for most triangular configurations, around the equality scale, it corresponds to an FNL of order a few.
So the Doppler correction in the power spectrum of a single tracer, as we looked at before, is not detectable in the next generation surveys because the relativistic effects are too suppressed in the power spectrum of a single tracer. The bispectrum of a single tracer is less suppressed. It has a relativistic contribution, a Doppler type relativistic contribution that goes as h over k instead of h over k squared, what you get in the power spectrum, which means this is potentially detectable. And this correction comes from coupling between long scale and short scale modes. So what we've done is a simple signal to noise ratio forecast. So this is a simplified assumption still. There are other things that would need to be included, like a window function, for example, and also we assume a simple Gaussian variance with uncorrelated triangles. And we include only the leading order h over k contributions, which also means that our variance is simply equal to a Newtonian variance because relativistic contributions to the variance come in as h over k squared. So what this really just is a summation over all triangle shapes, so that's all values of k, all k modes that are included in the survey, and all orientations of this triangle, so all values of mu1 and phi. And then it's simply the bispectrum squared over the variance, where you need to take the complex conjugate because this is an imaginary bispectrum. So if we first look at a stage 4 H-alpha survey, so something similar to Euclid, we are using the Euclid 2019 specifications for our survey, and we're using Planck 2018 best fit parameters for lambda CDM. As it turns out, the bispectrum for a spectroscopic survey is very similar to changes in the evolution and magnification bias, which are B, E, and Q. And it's very important to model these self-consistently from the same luminosity function that produces the number density. And that's what we have done. And we've plotted the evolution and magnification biases in the plot on the right-hand side. Then these plots show the signal-to-noise ratio that we've obtained for our spectroscopic survey. So the plot on the left-hand side, the upper panel, is the signal-to-noise ratio per redshift bin. The cumulative signal-to-noise ratio for this survey is on the plot on the right-hand side, and it goes up to, over the entire redshift range that we considered for this Euclid-like survey, goes up to a signal-to-noise ratio of around 18, which points towards potential detectability of this in a galaxy survey. Now it turns out that our signal-to-noise ratio is quite sensitive to K max, which is your maximum K or your smallest scale that you're probing. And we have used a conservative redshift dependent Kmax for this. So Kmax is roughly where your perturbation theory will start to break down.
So some questions we could ask are, Are the long wavelength modes crucial for this? Do we really have to measure the very longest wavelength modes in our survey in order to detect this? Naively, you would think that this would be the case, but actually the effect of the longest modes are actually rather weak. So if we change the minimum wavelength that comes into our signal to noise calculation compared to the fundamental mode of the survey, we can see that if we change that by a full order of magnitude, it only drops the signal to noise by less than a factor of 2. So the longest wavelength mode is not that important actually for the full signal to be detected. And this is again because the relativistic signal kind of rides on top of the Newtonian one, which boosts it significantly. Are second order effects important? Well, this is easy to see because we can just do the same calculation for the signal to noise, but just not include the second order effects. Turns out this reduces the signal by nearly a factor of 2. So yes, ignoring the second order contribution is not sufficient to get an accurate answer. Furthermore, it means that detecting the signal is a way to detect second order contributions.
So after looking at a galaxy survey like Euclid, let's now look at a 21 centimeter intensity mapping survey, so something similar like the SK. The way intensity mapping works is that instead of looking directly at galaxies, you're looking at integrated radio emission by galaxies, so you get an integrated sort of map of the universe. We're looking at Meerkat and the SK in single dish mode, and also look at Hyrax and Puma, which is still in proposal stage in interferometer mode. The good news about 21 centimeter intensity mapping is that your evolution and magnification biases are a lot simpler in expression. However, your signal is significantly weakened by foreground removal and by telescope beam effects, which is a big downside in intensity mapping surveys. So let's first look at the single dish surveys. On the left-hand side again, here is the signal to noise ratio per redshift bin for Meerkat and for the SK, and on the right-hand side is shown their cumulative signal to noise ratios. And what you can see is that for SK, band 1 and 2 combined, you would get a signal to noise ratio of around 6, which really is a lot lower than Euclid was. And for Meerkat, combined with 2 different bands, you get an even lower signal to noise ratio of only around 3. Which maybe is detectable, but it's really not such good news. And the reason it's so much lower is really because of these effects that I just mentioned, from like the foreground removal and from the telescope beam, because that removes a lot of modes that were carrying a lot of signal. And that's really rather unfortunate, and something that we explored is that even if you would have a more optimistic foreground reconstruction, you still don't regain that much of your signal, so that's really rather unfortunate. If you then look instead at interferometer mode surveys, where we need to do some reconstruction, because from this interferometer you need to also apply a wedge correction to your data, which is what this NW signifies, where 0 is the most optimistic case, the best reconstruction we can do, that's blue lines, and W equals 3 is the most pessimistic case, is when we really cannot recover any data that's lost. You can see that for Hyrax, which is on the left-hand side, you get a cumulative signal-to-noise ratio of around 5, which is maybe, again, marginally detectable. And for Puma, which is a massive survey in proposal stage, it's starting to look a bit more optimistic. You go up to a signal-to-noise ratio of around 14 in the most optimistic case. However, Puma is of course rather futuristic and still in proposal stage, so it is still not such very good news.
So just to summarise then, we've shown that the galaxy bispectrum has large-scale relativistic effects, which appear at order h over k compared to h over k squared in the power spectrum. The main effect is from local Doppler type corrections and gravitational redshift corrections, which are coupled together.
The primary contribution is called the dipole, which comes from the purely imaginary part of the bispectrum, and this is something that we can maybe detect in these next generation surveys, in a galaxy survey better than in an intensity mapping survey, as we've seen. Thanks. I can't say fundamental. Fundamental.